Everyone assumes an industrial civilization, 100 light years away, would betray itself the way we do. Radio leakage, faint city glow, the soft chemistry of a breathable sky. None of that travels. The only industrial species we could realistically detect from that distance are the ones violently drilling, melting, or detonating their way out through miles of planetary ice. Not whispers, scars. And we are, at this moment, looking for exactly the wrong thing. Begin with the geometry of failure. A television broadcast leaving Earth in 1980 reaches a 100 light-year sphere with its signal strength reduced by a factor of roughly 10 to the 32nd power. By the time it crosses that distance, it is thinner than the cosmic microwave background. No instrument we have built or have credibly proposed can resolve it. The square kilometer array, even at full sensitivity, would not pull a sister Earth's accidental radio leakage out of the noise at that range. City lights fare worse. The combined night-side glow of every human settlement registers from 100 light years at roughly 10 to the minus 24th watts per square meter at the receiver. That is not faint, that is gone. Atmospheric biosignatures, oxygen, methane, the disequilibrium pair, require a transit geometry we will rarely get, and integration times measured in hundreds of hours per target, which leaves a strange forensic question. If a civilization exists out there right now, industrially active, thermodynamically loud, what is the one thing about it that could possibly reach us? The answer is not subtle. Consider where intelligence is statistically most likely to arise. Not on dry, sunlit surfaces like ours. Surfaces are rare. The dominant habitable real estate in this galaxy sits under ice. Europa, Enceladus, Titan's subsurface, and the countless analogues orbiting red dwarfs whose surfaces have been stripped bare by stellar flares. Tidal heating runs for billions of years without pause. The ocean is shielded from radiation. Chemistry is stable. If biology favors persistence, the subsurface ocean is the standard cradle, and our open sky existence is the cosmic anomaly. Now picture what an industrial species looks like there. No radio horizon, no night sky to broadcast into. Their entire technological development happens inside a sealed shell of water ice 10 to 30 kilometers thick. For most of their history, they are invisible by definition. The shell is the Faraday cage, the atmosphere, the ceiling of imagination. Then something changes. They build heat, they concentrate energy, they start cutting upward. The first time a civilization breaches its own ice, it does not whisper, it vents. And venting from 100 light years has a specific spectral signature. A breakout plume is not subtle physics. Liquid water under pressure released into vacuum, flash freezes and flash vaporizes simultaneously, producing a cryovolcanic geyser hundreds of kilometers tall. Add industrial heat, fusion exhaust, fission waste, concentrated solar redirected downward to cut the ice, and the plume carries a thermal anomaly that a passive moon should not have. Specifically, an excess at 8 to 13 microns, sustained, localized, and chemically wrong. Natural cryovolcanism on Enceladus peaks near 180 Kelvin at the Tiger Stripes. An industrial breakout would push 400 to 600 Kelvin in a region a few kilometers across, with trace emissions of fluorinated compounds, tritiated water, or noble gas ratios that no geology produces. The James Webb Space Telescope can already resolve thermal anomalies of that magnitude on bodies inside our own system. Scaled up, a 30-meter class infrared interferometer in the 2040s envelope, and the same signature becomes detectable on icy moons orbiting stars within 100 light-years. Some theorists suggest we have already imaged candidates and filed them as unexplained outgassing. The instruments saw. The classification failed. The Drake equation, as written in 1961, assumes a surface civilization that broadcasts. Every variable downstream of F sub c, the fraction that develops detectable communication, was calibrated to radio. If the dominant industrial species are ice-locked, F sub c does not just shrink, it changes units. It becomes the fraction that breaches, multiplied by the duration of the breakout event, divided by the orbital period during which the plume is visible from our line of sight. A civilization might be loud for a century and silent for 1,000,000 years on either side. The detection window is not the lifetime of the species. It is the lifetime of the wound in the ice. Frank Drake's original F sub L, longevity, also fractures. A subsurface civilization can persist for geological epochs without ever being detectable, then vanish back beneath a refrozen crust without leaving a trace we could read at this distance. The great silence under this model is not absence, it is phase. We are listening for voices in a universe whose dominant intelligences communicate, if at all, by cutting holes in their own sky, and most of those holes have already healed shut. So the answer to what an industrial civilization looks like from 100 light-years is not a signal. It is a thermal scar on an icy moon, lasting a few centuries, surrounded by isotopes that no chemistry should produce. We are not alone because the sky is empty. We are alone because we have been studying the wrong surfaces with the wrong filters for the wrong duration. If you have followed this series, you already know which moon in our own system shows a 197 Kelvin hotspot at its south pole that no model has fully accounted for since Cassini's 2005 flyby.